Hi, my name is Dominique Stonebot, and I will be presenting on reconstructing high altitude data from low Earth orbit using machine learning. I will go over an introduction, methodology, results and validation, and future work section. What is the problem? It is not understood exactly how charged particles leave out of their trapped trajectories in the radiation belts and scatter into the Earth's atmosphere. In order to obtain a predictive model of space weather, an established connection between low Earth orbit or LEO and high altitude equatorial spacecraft is necessary. Why should we care? The ability to predict space weather has become important as satellite infrastructure is vulnerable to energetic electrons. LEO is an accessible and cost-effective option, and there's no current in situ high altitude radiation belt monitor measuring equatorial fluxes. For this model, I used 12,567 conjunctions between POSE and RBSP. POSE measures precipitating electrons in LEO, and RBSP measured trap electrons in high altitude. The goal of this machine learning project aims to predict the observations of the recently concluded RBSP from the observations of POSE and LEO. Since the two spacecraft observed the same particle population, the resulting pitch angle distribution should be continuous for each conjunction. Here I am showing a candidate conjunction used later in the testing of the model with the observed flux from POSE and RBSP plotted in blue asterisks as a function of pitch angle. For this model, I used two POSE flux measurements, conjunction date number, coefficient of determination for the initial fit, L shell, magnetic local time, AE index, and AE star values for each conjunction as the predictor variables for the artificial neural network. Then I trained the model. I ran the training data set through the multi-layer perception regressor. I defined the activation function, which effectively excites the neurons to be hyperbolic tan. I also set the number of hidden layers to 3 and the size of each layer to 150, 100, and 50 respectively. When implementing the backpropagation algorithm, I chose the stochastic gradient descent solver to optimize the weights of the model and minimize the cost function. So how well did the model perform? This figure shows the same pitch angle distribution for October 12, 2016, with the distribution from the model's prediction in black added. With no input from RBSP, the model predicted the CNN values to be 6.91 and 3.16. This predicted fit had a coefficient of determination of 0.93 and therefore indicates the model can predict high altitude data from LEO data. The panel on the left is a scatter plot of the predicted values against the test values, with N in magenta and C in green, closely following the y equals x line. The panel on the right contains the regression error characteristic or REC curve. As the relative error in the prediction increases, the percentage of correct predictions quickly tends to 100% for N, with C closely following behind. Using the SkyKit Learn Metrics module, I then returned various different error metrics shown in the bottom right corner. While the present model is not perfect, it is very close. And finally, future work. With promising results, I hope to expand the study by including other Van Allen probes and POSE satellites and exploring other energy channels. I also plan to investigate other areas where the L shell is less than 3. Here are my references, and thank you.